Hi, I want to talk about the two-dimensional motion problem that we're going to spend the most time discussing in this course, and that's the case of projectile motion. And I think of projectile motion as free fall plus, because the conditions are exactly the same as free fall, but we get one more component. And in free fall, our fundamental concept is that the only force is gravity. Well, applying Newton's second law, the acceleration we would get would be minus the strength of gravity in our y direction j hat. Or we could write it as 0 I hat minus g j hat, and we could even write plus 0 k hat. But here's how we normally frame the problem. Because our only force is gravity, we can always think of two perpendicular directions. One is the direction of forward motion. So whichever way the particle will be projecting forward. The other is the axis of gravity, which is the line along which gravity is currently acting. So in that perspective, we don't need a third dimension as long as we sort of frame ourselves to thinking about we're going forward in the x, gravity is affecting us up and down, well, down, in the y direction. So, if we look at our equations of motion, we have constant accelerations. In the x direction, we have a constant acceleration of 0. So there really is only one equation of motion. The displacement in the x direction is equal to our speed in the x direction times time. And that speed has to remain constant because there are no forces in that direction to change the motion in that direction. Now in the y direction, we have a constant acceleration of minus g. So if we were to go through the one-dimensional kinematic equations and replace our acceleration everywhere with minus g, we would get the following family of equations. If we don't know our displacement, our change in y, our final velocity in the y direction would be equal to our initial velocity in the y direction minus the strength of gravity times time. And remember, g, the strength of gravity, is always, always, always a scalar number that is inherently positive amount. Now, if we don't know our final velocity in the y direction, our displacement in the y direction will be our initial velocity in the y direction times time minus 1/2 times the strength of gravity times time squared. If we don't know our initial velocity, though, we'd start at the end and then undo the change due to gravity. So our displacement would be v final in the y direction times time plus 1/2 times the strength of gravity times time squared. And if we don't know anything about time, our displacement in the y direction would be our final velocity in the y direction squared minus our initial velocity in the y direction squared divided by -2 times the strength of gravity. And sure, we can always say that our displacement would be our initial velocity or final velocity, add them together, divide by 2, and multiply by time. But often, if we're dealing with projectile motion, we usually know what planet we're solving this problem on, and if it's Earth, the strength of gravity is typically going to be 9.8 meters per second squared. But, as I said, this equation still applies. We're just not going to use it very often at all. Now, a lot of times, we're given initial information about a projectile based on how fast it's traveling and the angle that it makes with the horizontal direction, the direction of forward motion. So if that's the case, where we know an initial speed and an angle, then the x component of our velocity would just be that speed times the cosine of that angle, provided that it is the angle from the direction of forward motion. Again, sometimes we get the angle from the vertical, the angle from the axis of gravity. So if that's the case, we would have something a little bit different. Draw careful pictures before you do your trig. Now the initial velocity in the y direction, if we're measuring off the horizon, off the direction of forward travel, the initial velocity in the y direction is going to be our initial speed times the sine of the launch angle. Thanks for watching.